You want to detect a pothole. Think of these hidden layer neurons as some junior analysts who are working, and one person is just looking at a round patch. The other person is looking for surface cracks, another is looking for debris, another is looking for depth, leaks, things like that, right? And then they go to the hidden layer 2, which is like their manager. And he says, yeah, I found 0.5 chance of a round patch plus 0.6 chance of a surface crack. Then some activation function in this layer clicks, right? And same thing, this manager is looking for leaks and depths and something else. And then they go back to their boss and say that, okay, based on my activation function is yes, and this person says mine is no. And then let's say the boss has some overall weightage of this manager's activation function 0.5 plus this or 0.5. Based on that, they say, yeah, this is a priority, we need to go and fix it. This is how a neural network would look if people were doing this individual task. Except in traditional machine learning, like this round patch, surface crack, we call them features. So we create different features and then we run a machine learning algorithm. As opposed to in deep learning, these features are figured out within the network itself. So while I'm calling out this as a round patch, we don't really know which of those neurons correlate to a round patch versus a surface crack. Some of those do, and then we go get the answer.
It's pretty simple. If you can actually illustrate an equation, you're machine learning. If you can't illustrate the equation, you're deep learning. And so it is really about knowing your inputs, your outputs, your variables, and the different pathways that you've actually structured to get to machine learning. Whereas deep learning is, hey, give me the data and I'll tell you what I tell you. The opacity of deep learning models is one of the reasons why the medical industry was really hesitant to use them.
I was doing square roots with my 10-year-old daughter. So what is the square root of 256, right? And she doesn't know. She doesn't know all these tables beyond 10 or something, right? And then one of the ways is like, you try like, what is the square of 5? 25. Okay, so it needs to be a number that is bigger than that. Let's try 10, 100. We are still not close to 256. Let's try 20, 400. Okay, that's too big. So we need to come down now. We went from 5 to 10, and then 10 to 20, and then we said, let's try 18. And then you come down and then you find. Right? Like when a mathematician is solving a problem, they are using an equation. When a computer scientist is solving a problem, they will say, I will just try to approximate based on is the loss in the negative direction or positive direction. And based on that, I will change my weights. And then I will see how far am I from the loss, and based on that, I will take a step. So those are the ideas behind backpropagation on how do you get the feedback and how do you move towards that approximate solution. And then in this case, you will get the exact number for 256. But if you have like multiple variables and multiple combinations, you would never get an exact answer, but you will get a close enough answer with 99% accuracy. You can tell whether it's a cancerous cell or not. Like that's the intuition behind how the learning works behind this.